Okay, so we're going to start with Chapter 4 in AP Physics here on dynamics, Newton's laws of motion. So I'm going to give you a quick little introduction, and you'll learn more about it as we do problems together. But the big thing we want to talk about when we start with Newton's laws of motion, let's first introduce the concept of force. So force, as you might be familiar with, is a push or pull. Pretty simple, push or pull. That's a H. It looks sort of like a K, but we'll make it an H. Now it looks weird. Okay, so just in a simple sense, like push or pull. So if you have a box, and if I'm pulling on it with a force F, I can, if under just simple circumstances, I could cause the box to move. The same could be said with, you would not know the difference if you then took that force and made it become a push. So either one of those would work out, and it would both have the same result. So force is measured in newtons. So we're going to talk about this. This is a derived unit, which comes from the force the force needed to accelerate a box, a 1 kilogram box, at 1 meter per second squared. So it ends up being that force has units of newtons, and that ends up being a kilogram times a meter per second squared, and so we end up calling that a newton. So both of these are equivalent right here, and that's pretty simple to understand. So a big thing you need to get is that when you think newton, I want you to think back to the derived units of kilogram times meters per second squared. So that leads us to this concept of Newton's second law, where we have the summation of forces. I'll come back to Newton's first law, is equal to the mass times its acceleration.
Excuse me, an interruption.
And so we have two vector quantities here, force and acceleration. And so this sort of reiterates that concept, or that when you have a scalar quantity, mass, in this case, multiplied by a vector quantity, you end up getting a vector back. So what does this say, Newton's second law? It's pretty simple. It's just stating that if you sum all the forces acting on a body, then it would be equivalent to that body's mass times its acceleration. So let's just take a what if. So if we had that pull again, the force F, and that was pulling the object to the right, but then there's a frictional force, and I'll actually just make it a different color. Let's make it like a green, and so this is pulling this way to the left, and if we knew the value, so we'll call that force of friction. I think you know that enough now, and this would be, we'll call it force applied. I'll go back to red, so if you were to sum these forces together, so if you look at the diagram here, so if you sum the forces along the x, then you would end up having the force applied minus the force of friction, and you're actually adding them, but as we know, if we call force applied positive, then force of friction has to be the negative of that, because it's pulling in the exact opposite direction. And since force is a vector, that would be a negative quantity, and that would be equal to that box's, and we'll put that m right there. That box's mass times its acceleration. And so this is the sum of the forces, and then the sum of those forces is equal to its mass times its acceleration. So that's the basics of this chapter, is that we're just going to be figuring out how to sum these forces and then put them together to solve for different aspects of a system. So we have the system of particles, or objects, and so you could end up having, like, for instance, a system where, let's just take a simple system like this, where you have a rope attached to that goes over a pulley, and then you have a mass here and a mass here, and so here we have a system of objects or particles, and then we are charged with figuring out the acceleration on this system or something. So, for instance, what is the net force? Oh, and by the way, I always think summation of forces, but F net is the force that you have after you've summed all your forces. So in a way, you could sort of say that that's basically the same thing as saying summation of forces. So after you've summed all your forces, you get F net. And whichever way F net is going, then we know that F net's direction, oh sorry, I didn't want to write an equal sign there, direction is the same as acceleration. So it equals the acceleration direction. So if F net was to the left, then the object is accelerating to the left. You know, you get the idea. And that'll come into play more especially when we talk about circular motion. So going back, there's Newton's second law. And then going forward from here, the first law, I'll just write right here. I'm just going to write this word inertia for you. And that is resistance to change. And so I'll talk about this in class more, but because there's no reason for me to use the time here. It's a pretty simple concept. It basically is, you know, that this definition already, that an object in motion will remain in motion, an object at rest will remain at rest unless acted upon by an outside force, an external force to the system. So if you have an object moving, it doesn't need a force to keep it moving, but if you have an outside force come and act on it, then it will change the direction, or it could take away the motion, the movement. So that's the concept of inertia. And then the third law, which I'm just going to briefly mention here, and again, I'll pay these much more, and they deserve much more attention in class. It's easier just to talk briefly with you in person. But the third law is that for every force that acts, if one object exerts a force on another object, then if A exerts a force on B, then B must exert an equal and opposite force on A. So force of A on B is going to equal the negative, or equal the force of, let me see if I can get rid of that. There we go, get rid of that mark down there too. The force of B on A. But of course, one would have to be negative in order to assure that one's going in the opposite direction. So you might have heard it as there, for every action there is an equal and opposite reaction. So, but this also says that forces must come in pairs. You can't have one force without a force pair with it. And when we get to free body diagrams, and we'll do those in class quite easily, then you'll understand how to put all these force pairs together when you actually diagram the problems and try to solve it. So, so the first law, the concept of inertia, you know, that concept that an object will continue in a motion or stay at rest unless it's acted upon by an outside net force. That's the key. It has to be a net force. Second law, summation of forces equal ma. Third law, that just that simple concept that a force exerted on one force that if an object exerts a force on one object, that object has to exert a force back equal and opposite to the force that was exerted on it. And so that gets us to some simple ideas here. And I'll wrap up with just some other little concepts of forces. So a restatement of Newton's second law is weight. W-E-I-G-H-T. And weight is equal to an object's mass times little g, or acceleration due to gravity. And this weight is dependent upon the acceleration of a gravitational body, or such as Earth. But what would happen if you went to the moon, where g is 1/6 g? So it would be the same formula, except for now it would look like this. Your weight would now be W equals m, I'll use m for mass now, times 1/6 g. What if you went to some planet X, where g is 10 times that of Earth? So now your weight would be 10 g. So you just substitute in for what g is and m, and you now have your weight. So let's see what weight would be measured in. Let's think. Well, what are the units of mass? Kilogram. What are the units of acceleration due to gravity? Meters per second squared. So I told you to think about that, and what is that? That is a Newton. So weight is measured in newtons. Now think, and don't get confused here. You don't want to talk about mass as being weight. So I want you, when it gives you a weight, then you need to talk about it in newtons, and you can always figure out its mass because you know what g is on Earth, for instance, and you could just divide and get the mass. All right, that's the basics of the setup here. I got about 2 or 3 minutes, so I'm just going to start talking about setting up some problems. So what would happen if we had a box sitting on a table and it's at rest? So its inertial reference, it's at rest, and we're going to talk about free body diagrams, and we'll get started on those right now. So I'm going to have to actually move that. So I'm going to put it down here. So what are the forces acting on that body? So notice free body. So I'm going to free it of that body and make a diagram down here that's free of the actual diagram. So here, this makes it easier to look at. So what's pulling that box down? Well, that would be the weight of the object. Now weight is equal to mg. I like to use mg for to label the force pulling it straight downward. In this case, the weight, which is the force of gravity on that mass. And then equal and opposite to that, and notice I try to make the magnitudes of my two vectors equal in length, because remember, length represents magnitude, and the direction is indicated by the arrowhead. And this would be a new force called the normal force. And normal, if you look it up, the word normal just means perpendicular to. It certainly doesn't mean me. I think I'm anything but, well, I'm pretty normal. Okay, so we would have the force normal, and that's the table pushing back up on the box. So mg downward, and then the force normal pushing back upward. And so that is pretty simple. But now you could ask, well, what would happen if I had a box and there's a piece of string pulling it up, and with some tension? We'll call that force tension because it's tension in a string. And here it is sitting on the table, and then we had oh, I'm sorry, I have to I'm going to get to about 15 minutes and I'll be done. So now let's do the free body diagram on this. So we'd have, again, force normal, and then mg, and then we have over here, I'll put it parallel to it, but just displace just a little bit to the right, and I'm going to make it just a little bit less than force normal. So there we go, and that's the force of tension. So let me just let's do that summation of forces concept. Let's do a practice one. So what do we have here? Well, let's choose up to be positive. So I'm going to say we have force tension plus force normal minus mg, and all those together, according to Newton's second law, equal ma. Right? And so if the object is not moving off the table, what can we say about A? If it's just sitting there at rest still, we're pulling up on the box, but it's not moving. That's allowable. So then, therefore, A equals 0. So if A equals 0, then this term goes away, and then now the equation is equal to 0. So let's see how could we discover the force normal in this particular case. So let's see what we could do. Well, you'd say, well, force normal therefore equals, what happens if I move mg, negative mg, over to the other side? We now have positive mg. And what happens if I move positive ft over to the other side? We now have minus ft. So now the force normal would be equal to the weight pulling down on it minus the force normal. Oh, what? Okay, that makes no sense. Just a minute. I moved ft over and I wrote force normal. Sorry, minus the force of tension. Sorry about that. So that, and it sort of makes sense, doesn't it? So the normal force has decreased because you're lifting it up some, so the table can't push up on the box with as much force. Now the weight didn't change. The weight's still the same. It's just we reduced the amount of weight of force that the table is able to push back up on it. And I'm going to stop right there, guys. And that's a good setup right there. You remember, this is chapter 4 from your book, and you can look through the first couple pages. I think chapter 4 starts on page 72, and we got a decent amount done. All right, watch this over the weekend. I'll email you and remind you.